Hello fellow problem solvers, so today we're solving the problem for the 2025 European Girls Math Olympiad, problem number 1. I suggest you try this nice problem out for a minimum of 10 minutes, ideally 30 minutes to maybe 40-ish, but not more than 90 minutes. Now without further ado, let us begin. So we have these, a positive integer n, and C1 through Cm are the positive integers smaller than n that are relatively prime to it. And we must find all n's such that when you sum up these pairs, consecutive pairs of relatively prime numbers to n, their sum and n have some common factor other than 1. Okay, so the first thing we should do with these problems always is try to figure out, okay, so what happens if we say, look at n is equal to 2. We have, okay, for 2, there's nothing really. So let's start with n equals 3. For n equals 3, we have 1 plus 2. These are the co-primes, is equal to 3, so 3 works. Let's look at 4. For 4, we have the primes are 1 and 3. 1 plus 3 is equal to 4. Again, this works. So 4 is checked off. What about 5? Well, for 5, we have 1 plus 2 is equal to 3. But 3 and 5 have nothing in common, so this does not work. So now let's continue. Again, always, let's continue on playing around until we find something. So for 6, we have 1 plus 5 is equal to 6, so 6 works. Is equal to 6 works. So we have 3, 4, 6 work. Okay, sort of 5 doesn't work. What about 7? N equals 7. We have 1 plus 2 again is 3, so this does not work. N is equal to 8. What do we have? We have that 1, 3, 5, 7 are relatively prime. 1 plus 3 is 4. 3 plus 5 is 8. 5 plus 7 is 12. All have a 2 in common with 8. And let us continue onwards even. So let's say now look at n equals 9. Again, the main idea here is you play around with some small cases, and then you see at what point do you get a idea for a general case. So let's continue onwards with 9. So with 9, what do we have? We have that, well, the relative prime is 1 plus 2 is 3. 3 and 9 have something in common. Then it's 2 plus 4, which is equal to 6. Again, something in common. 4 plus 5 is equal to 9. Again, we're good. Then 5 plus 7 is equal to 12. Again, we're good. And then 7 plus 8 is equal to 15. And we're good. N equals 10. What do we have? We have, here it's the 1, 3, 7, 9 are the relatively prime numbers. And every time you sum 2 of these up, you get an even one. So now here I invite you to pause for 5 minutes to try to push the problem further. And now when we try to push it further, like the first idea for me is some n which work are even n. And this is like, okay, quite straightforward. If you think about it, so you have, if n is of the form 2k, then all the relatively prime numbers, then ci and ci plus 1, they're all odd. So their sum, ci plus 1, is divisible by 2. And now their sum is divisible by 2, well then, the GCD of 2k and ci plus 1 is at least going to be equal to 2. In other words, this is divisible by 2. And so we know that even n work. Now for the odd n, what do we see? We saw, so primes did not work out, but 3 and 9 worked out. And now, the next question is, okay, why don't primes work out? Well, what do we really see initially? We see that, so if this is an odd number, then C1 is going to equal 1, and C2 will equal 2. And then C1 plus C2 is equal to 3. And the GCD, if this is to work, the GCD of n and 3 must not be equal to 1. But if it's n and 3, this can only equal 3. So 3 must divide n. So now we have, okay, n is divisible by 3. This needs to hold true if n is odd. And now the question is, okay, do the numbers that are divisible by 2 and 3, are those the ones that work? Or is there something else going on? So let's continue by now exploring. What about the number 15? What do we have for 15? So that's 3 times 5. We're looking at the next smallest number that is odd, divisible by 3, and to see like, okay, is it just, like, is this enough? Is it enough for it to be divisible by 3? What happens with 15? Well, we have the coprimes are 1, 2, and after 2 we get 4. Again, will be good because of divisibility by 6. And after 4 we get 7. And now we're in a pickle because, okay, 4 plus 7 is 11. And this does not work. So for some reason, okay, 15 doesn't work. What about 21? Well, 21, what do we get? We get 1, 2, it works. 3 is introductory prime. 4 is, again, 2 plus 4 works. Now 5. 4 plus 5 is 9. And then we get 5, 6 isn't. 7 is relatively prime. We get 12. It works. And after 7 we get 8. 15, again it works. After that, actually no, we don't get 7, my bad. We don't get 7. We get, after 5 we get 8. And now it's 13, and this does not work. Some of these is 13. Doesn't work out. Okay, so here we had like, are there any similarities here? This is a time to pause and check, so this was 3 times 5. This is 3 times 7. Like, is there something going on here? I mean, I'm saying, okay, this is 7 minus 2, 7 plus 1, 5, like, could that be it? But it doesn't work here. It's minus 1, plus 2. Doesn't quite work out. Let's look at 9. 3 times 9, which is 27. The next odd number divisible by 3. We get the numbers are 1, 2, 4, 5, 7, 8. I mean, this is a power of 3 to the third. So it's going to be every number which doesn't have a 3 in it. And they alternate with their remainders. It's 0, 1, like 1, 2, 1, 2, 1, 2 mod 3. So the sum of any two consecutive ones will be divisible by 3. And ergo, the GCD of 27 and then the sum of any two consecutive ones will have 3 as a common factor. So 27 works. And in fact, I invite you here to pause for 2 to 10 minutes and try to find out what other things work. And the answer is, well, if I take n is equal to 3 to the alpha, then my claim is that C2t plus 1 is congruent to 1, and C2t plus 2 is congruent to 2 modulo 3. And I mean, this is self-evident, I would say, because like we're skipping the numbers that are not divisible by 3. I wouldn't even try to prove this. And so their sum, ci plus 1, is divisible by 3. And now, and ergo, the GCD of n and ci plus 1 is divisible by 3, and ergo is not equal to 1. And so n is equal to 3 alpha also works. But now we had an issue with the other types of n. And now for this thing, so we can see, again, let's look at 33. Just to make sure there's no major mistake, no major thing that we overlook. So 33, we get 1, 2, maybe we can check it out. So it was 11 times 13. So let's maybe look at 11 minus 1 is 10. And then 11 plus 2 was, no, we won 12, we won 13. So 11 has something in common, and so does 12. So these are two consecutive relatively primes. And when you sum them up, you get 23. Okay. let's look at another number. So this time let's actually look at, we can look at 3 times 13, which is 39. And let's look at, okay, now say it's 11, then we have 12, 13, 14. So these two aren't co-prime, but 11 and 14 are. When you sum them up, you get 25. Again, relatively prime to this. Okay, so now let's think, before I even think about generalizing this, let's also look at a number that is divisible by 9. So 9 times 5 is 45. Let's see, where do we fail here? What is it that messes us up here? So if we go 1, 2, 4, not 6, 1, 2, 4, 7. Okay. 4 plus 7 messes us up. So now I invite you here to pause for 2 to 5 minutes and see if you can push the problem further and finish it up. And the major idea is quite simply, okay, I mean, there's 2 ways to solve it now. One way is like this motivated reasoning with playing around, which is a key problem solving principle that we come again and again to on this channel. And the idea is, okay, so let's say n is equal to 3 to the power of k times some t, where t is not divisible by 3. And now sort of our claim is like we're going to look at, okay, if t is congruent to 1 modulo 3, then we have t is equal to 3s plus 1. Okay? And then we know the number 3s minus 1 is going to be relatively prime to n. So 3s minus 1. We claim that the GCD of 3s minus 1 is relatively prime to n, and 3s plus 2 is relatively prime to n. So obviously 3 times s is not relatively prime because it has a 3 in common. And on the other hand, 3 times and 3s plus 1 is not relatively prime because n is of the form 3 to the power of k, 3s plus 1. So let's show that these two are relatively prime to n. And it's as simple as, okay, so let's say, I mean, there's multiple ways to go about this, but say that p divides this. So if p divides this number. So p, this obviously is not free, so p has to divide 3s plus 1. So then p has to divide their difference, which is p needs to divide 2. In other words, this can only be a prime number. And this can only be 2 as a prime. And so it doesn't work out. It's as simple, like, sometimes, you know, if you want quick way to show 2 numbers are co-prime, deal with prime factors instead of the whole Euclidean algorithm for GCDs, because that's what we want to show, co-primeness here. And now assume, okay, p divides 3s plus 2. Again, if p divides both of these, p cannot be, isn't free, so p has to divide this part over here, which means p divides this and this, so it divides their difference, which is 1, a contradiction. And p isn't 2 because both of these are odd numbers. And so now what we've shown is that these numbers are relatively prime to n. And now let's assume that, now let's look at their sum and prove that their sum is relatively prime to n. Well, their sum is equal to 6s plus 1. And now again, assume p divides this, p divides this. P is obviously not free, so p has to divide this part. Now p divides 3s plus 1 and 6s plus 1. This divides 6s plus 2. It divides the difference. P divides 1, a contradiction. And then the other case is pretty similar. So if t is congruent to 2 mod 3, then t is equal to 3s plus 2. And then we have n is equal to 3 to the power of k times 3s plus 2. And our claim is now that we're going to have what? 3s plus 1 and 3s plus 4 are going to be the ones that are relatively prime to it. And Again, if p divides this and this, it divides the difference. If p divides this and this, it divides the difference, which is 2. However, this number is odd. And so these two numbers are relatively prime to n. And then their sum is 6s plus 5. If p divides this, then p divides 6s plus 4. Now if it divides 6s plus 4 and 6s plus 5, then it divides what? 1. A contradiction because p is a prime. And ergo, we've shown that now all the numbers, like if n is of this form, where 3 does not divide t, then there exist two consecutive relatively prime numbers, 2n, such that their sum and n has a GCD of 1. And that finishes up the problem. Like, we've shown that evens work, we've shown that powers of 3 work, and now we've shown that every other number which doesn't have a 3 doesn't work, which isn't a power of 3 doesn't work. So, I mean, we've shown previously that the whole number had to be divisible by, if it's not divisible by 3, we get an immediate contradiction. Like, if it's odd, it has to be divisible by 3 because the first two numbers force it to be. And now I also want to talk a bit about a different type of solution, which I thought was more interesting in its own way, a different way of thinking, which is, I mean, we do the same thing for showing that evens work, that 2k works, that 3 to the k works. And now we say, let's assume that this number n has some other prime factors, p1, all the way till some ps, has these prime factors, and it has a 3, and it's divisible by 3. So now, okay, the idea is, again, well, can we construct now, like the question here is, can we construct two relatively prime numbers which aren't that far apart? So you want some ci and ci plus 1. You want to make it such that they're pretty close to each other, so that you can sort of make an argument that the numbers between them are going to be, the numbers between them are have something in common with n, and the less numbers there are between them, the easier that's going to be for you. And yeah, I think that's your most important thing, so you can show that this is actually the case. And obviously, so one of them is going to be divisible by 3, and maybe there's going to be the two of them, or maybe there's another number in between them. And now it's thinking about, okay, how do I construct these numbers? So one way is to say, okay, let me construct, let's say that numbers are going to be 3 times s, and this is going to be 3s minus 1, 3s plus 1. Let's say that I can construct these two numbers, right? So what do I need? I need to show that there's two numbers which are both relatively prime to n, and that are neighbors like this. And now, okay, so like if I'm constructing this number, what do I need for this number to hold? I need, if this number is now my q that I want to construct, I need q to be congruent to 2 modulo 3. What else do I need? And if I have that, I'm doing well. And I also want q to have, so I want pi to not divide q, and I want it not to divide q plus 2. So those are the two things I want for each I. So how can I make that a reality? And one idea is, okay, I'll set q to be congruent to -1 modulo each pi. Okay, each one of these prime factors, they are different than 3, and it's not 2 either. And then q plus 2 is going to be congruent to 1 modulo pi. And now, what is going to be important here? So here, what we're going to have then is two numbers now such that you have then q plus 1 is divisible by all of these numbers, by p1 through ps, and it's divisible by 3, but q minus 1 and q plus 1 are not. And so we're done, right? No, we're not. Because if n was equal to 3 times p1 through ps, you would have a problem, because then q plus 1 would in fact be n. And you wouldn't really have anything, right? Because then q... Actually, no, q would be... Yeah, q plus 1 would be n, and then you wouldn't really have anything with these other numbers. So now you need a different approach. The problem you had here was that so if n is not square of 3, you're done. But now the question is, okay, what if n is square of 3? And you still need to somehow construct these numbers. And now the question is, okay, the real issue here that we had was that everything sort of, like, we had a lot of things that held for this number over here in between them. But we can also just construct an extra number. So we could have q plus 1, q plus 2, and q plus 3. We could set, say, this number to be divisible by 3, and this number to have all the other pi's, p1 through ps. And so let's set that up. So q is congruent to minus 2 modulo pi, and q is congruent to 2 modulo 3. And now, what do we know? And now we know about the number that both. So now what happens to q plus 3? Q plus 3 is not going to be divisible by any of the pi, and neither is q. Q plus 2 is going to be divisible by all of the pi's, and q plus 1 by only one of them. But again, now the question is, can we guarantee that this number is going to be small enough, right? Can we actually guarantee this? Because this is a type of number, like, so we have, basically we just took the product of all the pi's, p1 through ps. If this product was p, then basically 1q is equal to, q can either be p minus 2, 2p minus 4. Yeah, it's either one of these two things, right? Actually, no, that's 2p minus 4. Actually, no, yes, I think it's... So if it's p minus 2, it's either, yeah, or 2p minus 4. Because then q plus 1 in this instance is... q plus 1 in this instance is equal to p minus 1. And here q plus 1 is equal to 2p minus 3. In other words, actually, it cannot be this. So it could be the fact, by the Chinese remainder theorem, that we get that in fact q plus 1 is equal to 3p minus 5. And I'm getting a sense that, again, potentially could we have an issue? Or not, maybe we don't. Maybe we don't have an issue here. So let me just double check this. If q is equal to this, actually no, q is not equal to that. Q is equal to, oh no, q plus 2, my bad. So here, q plus 2 is either equal to p, 2p, p or 2p, and then q is going to equal p minus 2, or q is equal to 2p minus 2. In other words, we're going to have that q plus 1 is equal to, okay, p minus 1, or q plus 1 is going to equal to 2p minus 1. In either case, one of these is divisible by 3. And the important bit here is that we have that q plus 3 is also relatively prime to it, because q plus 3, I mean, in either of these cases, q plus 3 is not divisible by any of these, and it gives a remainder of 2 when divided by 3. And that finishes up the problem. Now you could also construct this in a different way to give these two numbers more. Switch up the factors in any way, shape, or form you wanted. But the major sort of sticking point here is you also want size constraints. You want to make sure that the size of this number, you have this number by the Chinese remainder theorem, but you want to be cognizant of the potential size constraints. And that finishes up this problem. I think it's a very, very cool little problem, intro-ish problem in number theory, and I hope you enjoyed it. Let me know if you have any other solutions or any other approaches that you tried out. And as always, thanks for problem solving.